Thank you. I'm Paul Gray, Professor of Electrical Engineering and President Emeritus, and it is my great pleasure to welcome all of you this evening to the 5th Ford Motor Company MIT Nobel Laureate Lecture. The Ford Motor Company has sponsored now for, this is the 3rd year, these lectures, and we are much appreciative of that support. As you know from the program announcement, our subject tonight is global environmental issues, effects on the atmosphere and the biosphere. Our first speaker is Professor Mario Molina. Professor Molina is an institute professor at MIT. If you're not familiar with that title, there are at any one time fewer than 12 individuals who are elected by their faculty peers to be institute professors, and they have the freedom of the house, so to speak. They are no longer confined to a department or a school, but may pursue their interests wherever it leads them. Professor Molina came to MIT in 1989 with joint appointments in the Department of Chemistry and in the Department of Earth, Atmospheric, and other planetary sciences. He shared the 1995 Nobel Prize in Chemistry for his work on the chemistry of the ozone layer and the effect of CFCs, chlorinated fluorocarbons, on the ozone layer. His interests now involve the chemistry of air pollution of the lower atmosphere, in particular the problems of rapidly growing cities. And those of you who have traveled recently to Mexico City or Bangkok or Beijing will know what that problem is. I should announce, if you didn't see it in Tech Talk today, that Professor Molina was a recipient of the Heinz Award just a few days ago for his work in the understanding and mitigating effects on air pollution and advocating changes in public policy as they bear on air pollution. Our second speaker tonight is Professor Eric Chivian. Dr. Chivian was co-founder of the organization called International Physicians for the Prevention of Nuclear War, an organization formed some 20 years ago, about the time Dr. Chivian joined the MIT staff as a physician in our medical department. That group, the organization, received the Nobel Peace Prize in 1985. Dr. Chivian is now director of the Center for Health and Global Environment at the Harvard Medical School. And his interests include the human health consequences of habitat degradation, species extinction, and biodiversity loss. Now, our plan for this program is that each of our speakers will speak for some time at the lectern, and when they are both finished, they will move to the table, and we will entertain questions from the audience. Please join me in welcoming Professor Molina and Dr. Chivian.
Thank you. Thank you very much, Professor Gray, for your kind introduction. It's a pleasure for me to be here tonight as part of this Ford MIT Nobel Laureate Lectures Series and to share the podium with my colleague, Eric Chivian. I would also like to thank all of you for being here in spite of the weather we have tonight. Maybe I'm presumptuous and you're all here because you got trapped with the snow. But I'm an optimist. I want to talk tonight about global environmental issues. So let me start with this overview of the sort of issues that we are concerned about. These are just examples. What I want to point out is we have two types of issues: depletion of natural resources, that includes issues such as loss of biodiversity and so on, disposal of hazardous waste, water pollution, air pollution, and so on. But we have another set of issues that I label global. And what's happening is that the first set of issues we normally consider to be local or regional. What has been happening in recent years is that these problems are happening in so many places on our planet that they are beginning to acquire global proportions. The second set of issues are truly global in scope because they are consequences of changes in the composition of the atmosphere truly on a global scale. So I'm going to say a few words about these aspects of environmental problems that have to do with the atmosphere. I think Eric will talk perhaps more about some of the biological effects. To put that in perspective, I'll show you this picture of our planet from space. We're dealing with the atmosphere. And what you really see from the atmosphere itself is just the clouds. The atmosphere is transparent, as you know. But the point I want to make here, it's very thin. It's like the skin of an apple. And that's why, on a scale of human activities, we can explain how is it that we are changing the composition of this very important system. Another reason why this is happening is that there are certain components of the atmosphere that we label trace gases that are present in parts per million or even parts per billion levels, very small amounts. But those are the ones that have important consequences for the behavior of the atmosphere itself. The bulk constituents, nitrogen and oxygen, are fairly inert in many of these physical and chemical respects. So I'm going to start talking about one of those problems that relates to a layer of the atmosphere that we cannot see here, which is the stratosphere. Before that, I want to point out another feature of this skin, if you want, this very thin layer, and it is the time scales for mixing. There are certain chemical compounds that, when released to the atmosphere, are very rapidly removed from the atmosphere by the cleansing mechanism that we have. Many of them are related to the presence of clouds. For example, rain removes many pollutants. There are, however, other compounds that last days, months, or even years in the atmosphere. The timescale for mixing within each hemisphere is of the order of months. That means if you release some compounds that are sufficiently stable to remain in the atmosphere for months of years, they will be rapidly mixed within each hemisphere. Mixing between the two hemispheres takes a little longer. The timescale is between a year or two. So let me move on to this problem. Oops. This problem that, the first one that I will deal with, which has to do with the ozone layer that our planet has. What we have here is just a typical ozone profile, and it shows concentration of ozone as a function of altitude. And ozone, this ozone layer exists in the stratosphere, which is the second layer above the Earth's surface. The troposphere is below. As I just mentioned, mixing in the troposphere occurs in very fast horizontally, a time scale of months. But the same thing happens on the vertical scale. Mix, if you release species close to the Earth's surface, it only takes weeks or months for them to be rapidly mixed throughout the troposphere. But in the stratosphere, mixing occurs much more slowly, and that's because temperature increases with altitude in the stratosphere, whereas it decreases with altitude in the troposphere. That's why as you go to higher altitudes, it gets colder and colder. So consequence of those temperature profiles is these time scales for mixing. Now, we worry a lot about the ozone layer because it has several very important functions. One, in fact, I just mentioned the fact that temperature increases with altitude and sets up the properties of the atmosphere. That's a consequence of the presence of ozone, which, by the way, is one of those trace constituents I just alluded to. It's present only at parts per million levels, just a trace amount. Ozone is a very unstable species. But its presence there, the consequence is to give this increasing temperature profile, and that's because ozone absorbs ultraviolet radiation from the sun. that would otherwise reach the Earth's surface and have very important biological effects. Some of that ultraviolet radiation at wavelengths between about 290 and 320 nanometers, what we call biologically UVB, or the biologically active ultraviolet region, that penetrates to the surface to some extent, depending on how much ozone you have overhead. But the point is that this is a very important component of a huge natural system. Now, what we have learned just in the past few decades, the research I started together with my colleague Sherry Rowlands in the 1970s, is that there are certain industrial compounds that we know as CFCs, chlorofluorocarbons. These compounds are not natural. They were developed industrially to replace toxic compounds like sulfur dioxide and ammonia for uses such as refrigeration. And they have several sets of properties. One is that they can be readily converted from liquids to vapors, and that's what you need in a refrigerator. They are also useful to make, for example, plastic foam, like the one you're sitting on, or as propellants in spray cans. All these uses require then this conversion of a liquid to a vapor, and vice versa. Second property is they are relatively simple to make and hence relatively cheap, and that's why they could be manufactured in large amounts industrially. But the third property, which is also very important, is that they are chemically very inert. You can even breathe them. In contrast to the gases they replaced, like ammonia and sulfur dioxide, you can breathe them like you do when you use a spray can, or at least that's what used to be the case in the past. Now, what we suggested in the 1970s is that the use of these gases would have important consequences, which are summarized in this cartoon here. What happens, because of the chemical stability, these compounds are not removed by these natural cleansing properties that the atmosphere has. They're not soluble in rain and so on, but they can actually move to the stratosphere. This is mixing here just takes a few months, but here it takes several years. And eventually, when they move above the ozone layer, they find the type of radiation that the ozone layer itself shields, and that's what breaks the molecules apart, releasing very reactive compounds that we call free radicals, and through an amplification factor, catalytic cycles, they can indeed affect ozone levels. So a single chlorine atom can actually destroy many tens of thousands of ozone molecules, and that's why even if you have only parts per billion levels of CFCs or of these compounds, you can have significant effects on ozone. So this was a prediction in the early 1970s. Many experiments were carried out, and eventually it became clear that something indeed was happening to the ozone layer, and of all places where the effects were most spectacular happened to be over Antarctica. As far as possible from the sources, these compounds were mostly released in the northern hemisphere. And what we have here is a normal-looking ozone profile, very similar to the one I just showed you a few minutes ago. And that was measured with balloons. Early in the spring, the light was just coming out in this year over Antarctica after the long polar night. And on a time scale of a couple of months, you could see that you develop this red profile, namely at some altitudes, more than 99% of the ozone was gone. Okay. So this is the consequence of this type of catalytic cycles I was mentioning. And these altitudes coincide with the presence of polar stratospheric clouds. I won't have time to go into the details of the chemistry that are very, very interesting, but let me just point out that this very spectacular effect occurs mostly at high latitudes, also occurs over the Arctic, although perhaps not quite as spectacular. But it became clear that ozone was being depleted not just over the poles, but at mid-latitudes as well. And what happened as a consequence of these findings and the scientific community working together, making a very strong scientific case, namely that the CFCs were decomposing in the stratosphere and in turn decomposing ozone, there was an international agreement called the Montreal Protocol, first enacted in 1987, but then strengthened, that led to a total ban in the industrial production of CFCs by the end of 1995. This ban happening only in the industrialized countries, but giving somewhat longer timetable for the developing countries to eventually ban the CFCs as well. So this is the first instance of a a truly international agreement that we believe has actually worked. And we can show that here. This is a set of measurements from one of the CFCs, CFC 11, by this L-gauge program, which is coordinated by my colleague Ron Preen at the EAPS department. And you can see here this very rapid industrial growth. The industrial production of these compounds led to increasing atmospheric concentrations of these compounds until it became clear that the Montreal Protocol was going to take effect. And around this time, then, industry essentially stopped producing these compounds except for these smaller amounts in the developing countries. And so you could see how the concentration is slowly coming down. What happens is it will take quite a few decades for these concentrations to come down because of the stability of these compounds implies that they will remain in the atmosphere for many decades. Because of this, we do not expect the ozone layer to recover immediately. It will take several decades more before we see, for example, the ozone hole over Antarctica disappear. But anyhow, this turning around in what is a global property of the atmosphere, a consequence of an international agreement, is the first instance that we have of such an impact. I'll come back briefly to this problem if I have time. But first I want to discuss briefly yet another problem which has to do with climate change and perhaps make some analogies with the problem of ozone depletion. And the problem of climate change, we're worried about it also because the chemical composition of the atmosphere is changing truly on a global scale. The problem has to do with the energy balance of our planet. And what we know happens in terms of energy is that our planet receives energy from the sun, but it's essentially a steady state, has been so for many millions of years. It loses essentially the same amount of energy as it receives from the sun. And those amounts of energy in this chart here are represented by the areas under these curves, which have to do with intensity of the radiation as a function of wavelength, or color if you want. So we receive energy from the sun, a good fraction of which is in the visible. That's why our vision developed has to have maximum sensitivity for visible light. But our planet loses this energy at much longer wavelengths in the ultraviolet. Now I have here several equations which I will not explain in much detail, but I put them here for historical reasons. These equations, for those of you that are physicists or chemists or engineers, you probably recognize them. They were developed at the beginning of the 20th century. They were extremely important. There was a revolution in physics that led to the development of quantum mechanics and so on, that names such as Albert Einstein or Max Planck are associated with these equations. So they had an enormous impact on the development of science, but it just so happens that Planck's equation also describes the shape of these curves. So this is very fundamental science, and in principle, we can use these equations to predict what should be the temperature of our planet. All we have to know is how much energy we receive from the sun, how far is our planet from the sun, and essentially also the color of our planet. And if we do this, realizing the sun is around 5,700 degrees centigrade, we calculate that the Earth should be at minus 18 degrees centigrade. And again, these are very fundamental equations. In principle, there's nothing wrong with them. But there's something wrong with the number. If we really had an average temperature in our planet of minus 18, the oceans would be frozen. We wouldn't be here. Okay. So there's something that requires explanation. But as experimentalists, we can see what else is going on in our solar system. The moon, on the average, is at the same distance from the sun as the Earth. And indeed, the moon, on the average, is at minus 18 degrees centigrade. So the calculation was all right. However, if you look a little bit more in detail, it turns out that on the sunny side, the moon is at 100 degrees centigrade. On the dark side, at minus 140 degrees centigrade. So on the average, it's indeed minus 18. Nice weather. Fortunately, the Earth back here has an atmosphere. Okay, so the atmosphere plays a very important role in terms of distributing this energy. But that still doesn't explain the average temperature that we should have. But we have another example. In this case, we go to Venus. Venus is, as you know, closer to the sun. This is a picture of Venus in the ultraviolet, because in the visible, Venus is very white. That's why you can see it so bright in the sky. So it turns out that the amount of energy absorbed by Venus, the amount of energy coming from the sun, is smaller than the amount of energy that our planet absorbs. In spite of that, the surface of Venus is very much warmer. It's around 470 degrees centigrade, okay? Warmer than a hot oven. And so this is because the atmosphere of Venus, in contrast to our atmosphere here on Earth, is very heavy, and it consists mostly of carbon dioxide. So what we understand now is what happens is Venus has a runaway greenhouse effect. And so let me just explain briefly then what this greenhouse effect is. The atmosphere, I already mentioned a very important function to distribute this energy coming from the sun. But another important function is that it functions as a blanket. It's transparent to the visible radiation coming from the sun, except for the presence of clouds. But it's not transparent to that energy emitted by the surface of the planet at much longer wavelengths. So that's why it functions like a cover, a mantle around the planet. And that's what explains this enormous temperature difference in Venus, and that's what explains why in our planet the Earth's surface is actually at plus 15 rather than minus 18 degrees centigrade. So that 33 degrees difference is what we call the natural greenhouse effect. And in fact, the minus 15 degrees centigrade temperature that we calculated is correct, except that it's not the temperature of the surface, which is what we care about, but it turns out to be the temperatures roughly 6 or 7 kilometers above the Earth's surface. So the greenhouse effect, from the point of view of fundamental physics, is very well understood. But here is what worries us. The gases that absorb this infrared radiation that I was alluding to are the so-called greenhouse gases. Their concentrations, for some of them, are being affected by human activities. And we can see here how carbon dioxide, its concentrations has been changing with time. So there is a different nomenclature that we normally use. We refer to the greenhouse effect. We label that whatever is changing as a consequence of human activities. What I just explained before, what happens in Venus and this 33 degrees difference on our planet is a natural greenhouse effect. But just the greenhouse effect, normally we use that phrase in connection with these changes resulting from human activities. Now, why is carbon dioxide increasing? First of all, you see these natural oscillations, and that's because it's biologically active. Respiration releases carbon dioxide, and photosynthesis absorbs it. So you see here the summer-winter variations in the concentration. The more pronounced ones are in the northern hemisphere, which is where the bulk of the landmass exists in our planet, and the less pronounced ones in the southern hemisphere, where there is less biological activity. But what jumps out here is this steady increase. And we know now, of course, where this is coming from. It's essentially from burning fossil fuels. Roughly half of the carbon dioxide, which is a result of combustion of these organic materials, ends up in the atmosphere. The other half is captured partially in the oceans, partly by the land and plants and so on. So let me give you another perspective for these changes. I discussed carbon dioxide now, but if we look back for a whole millennium, the year 1000 to 2000, and we look at the concentration, in this case, of 3 greenhouse gases. Here is carbon dioxide, here is methane, and nitrous oxide. Methane, you can see, also increasing very recently. Where does it come from? Turns out that methane is produced by anaerobic processes, bacterial processes. So a large source of methane comes from ruminants, from the guts of cattle, but also from growing rice. You have rice paddies that are flooded with water. So this is indirectly a consequence of human activities. And it's all very recent. Nitrous oxide is, to a large extent, produced by using fertilizers, nitrogen fertilizers. What is striking then is that these curves have a similar shape, and the changes began then with the Industrial Revolution. Well, there is one more curve that has a sort of similar shape. What we have here is temperature. Temperature in our planet, and this is the average, the mean surface temperature. You have to measure it in many places and then average it. The red line indicates direct measurements. But if we go back a whole millennium, there were no direct measurements. But there are ways to infer what the temperature was from tree rings, from corals, from ice cores, and even from historical records. So using our best understanding of all these pieces of information, one can reconstruct what the temperature was. Here it's actually constrained to the northern hemisphere where we have data. But what is quite clear is that you have this very recent temperature jump. So if we look at all these sets of figures, we might suspect that there's a connection between all of them. Well, but that connection turns out to be rather complicated because the climate system is complicated. So what I'm going to do is merely summarize it, and I'm going to use some of the conclusions of this so-called IPCC group, the Intergovernmental Panel on Climate Change. You can get here a little bit of information convened by the United Nations and so on, which, by the way, was established in a very similar way to the way we dealt with the ozone layer problem. There was an international community of scientists that provided assessments that were meant to advise politicians, and that's how the Montreal Protocol came about. This is a similar process, and this is one of the conclusions they reached, comes from calculations like the ones I'm going to describe briefly here. One way to look at the climate is through models of the climate that have to take into account all sorts of complications to the way the climate functions. Difficult models to build. That's only one tool. There are several other tools. But with those models, one can compute temperature changes. And this is done for the last, since, say, in this calculation from 1850 to the year 2000. And the lower line here is what is calculated to happen if you do not take into account these changes in the chemical composition of the atmosphere that I just showed you. If, however, you take that into account, then you get, instead of this lower curve, this other curve, and the upper line are the observations. So it's clear that these calculations fit the observations much better if you make a connection between those changes in the composition and what we expect to happen to the climate. If you have established or suspect at least this cause-effect relationship, then you can take one more step, and then you can predict what should the temperature do in this century once you make a connection between those two sets of observations. And what happens to the temperature in this century will depend on different scenarios. That is, it depends how society evolves, how the economy moves, and whether society imposes restrictions on emissions of carbon dioxide and other greenhouse gases or not. But what is striking here is that we have very significant temperature changes compared to what has happened in the last 1,000 years, and for that matter, in the last tens of thousands of years as well. So what do we do about this? First of all, we have to ask the question, so what? What happens if temperature changes? I will not discuss this in any detail, but just show it to you. There are, in fact, some beneficial impacts of a warming of the Earth's surface, like you might have longer growing seasons for some crops in some parts of the world. But overall, the effects tend to be negative. I've just talked about temperature, but rainfall will also change quite significantly if indeed these greenhouse gases have the effects that the scientific community is assuming. Sea level rise is yet another effect. So you have a multitude of potential effects, health impacts, that's one of the expertises of Dr. Chivian. But then you have agricultural impacts and water resources impacts. Obviously, if you change rain patterns, the consensus is that you might get, because of this temperature increase, more extreme events. When it rains, it pours. Otherwise, you have more droughts. So that's a logical consequence of having more moisture in the atmosphere. At this point, I should mention that water vapor itself is a very important greenhouse gas. So human activities will not directly change the amount of water in the atmosphere, But if through changes in carbon dioxide, the temperature changes, you have an important feedback effect, this water vapor will in turn enhance the greenhouse effect, and that's taken into account in these calculations. So you have other impacts. Sea level rise, of course, is very worrisome. Certain countries will disappear completely, the small island countries. What I'm doing here, I'll go through this very briefly, is just summarize what I've said so far in terms of climate change. We have certain, I would label these facts. The climate is clearly changing. Very few people doubt that. Okay. The atmospheric concentrations of greenhouse gases and other gases are clearly changing also. That's very well established. But what is perhaps less well established, but certainly very logical, is that these changes have a connection and that human activities are at least partly responsible for this temperature increase. And this last point just tells you the magnitude of these changes between 1.5 and roughly 6 degrees in this century, and some changes in the way this temperature is distributed. Okay. Let me ask a question here. With this information, what should society do? Should society do something about this problem? I recognize that there are uncertainties, or is it premature? Is it a matter of opinion? Well, let me clarify at least my own thinking here. What scientists can do is provide this type of information, but the actual answer to that question does not lie within the realm of science. It depends on your value judgments. It depends how you assess risks. But science can go at least one step further, and I'm showing you here the results of some very interesting calculations done by our colleagues here at MIT in the Center for Global Change Science, led by Professor Preen. What they have done is calculated probabilities. Since these changes in temperature are rather uncertain, you can at least assess, it's a little bit subjective. You cannot do this experiment. We have only one planet. But you can calculate probabilities based on what you think you know about the system. And here are the results. Two curves, one assuming that the society does something. Even if you do to take actions right now, you will have a temperature change because we already changed the composition of the atmosphere. But if you continue just with business as usual, you will have much larger changes. And then you can analyze this in any way you want. For example, there is one chance in 40 that the changes will be larger than 5 degrees. Those would be very, very large changes. They begin to be comparable to the changes between an ice age and an interglacial. Our planet would really look very different. Do you want to take that risk? Again, we only have one planet. But you don't have to go all the way to 5. What is most likely to happen is something above 2 degrees. Remind you that we already seen half a degree change, and we see all these consequences already. But there is one chance in 20 that you're going to be between 3 and 4. These are the sort of risks that we normally don't take. If I tell you there is one chance in 10 that you'll be stuck if you drive in the snow, only some of you might want to drive. But if I tell you that there's one chance in 10 that you're going to have a bad accident, you probably won't do the driving unless you have a very strong reason to do that. So again, this is not within the realm of science, considering we're dealing with the planet and we're dealing with these very important risks, and considering how many millions of people would be affected. In my own personal opinion, this is certainly enough reason to start doing something now, because the risks are just too large. And just to highlight one more point very briefly, I talked about average temperature changes, but the changes are not evenly distributed with latitude. You see that at the poles, you have some very large changes that could have very important consequences, for example, in terms of melting of the ice caps. Again, these are results from the group here at MIT. I'm going to transition now to the last problems that I will deal with. Let me try to do that fast, but I'm still talking about climate change, and here is just a representation of the forcings. That means how much do we expect on a relative basis different factors to affect the climate. And one factor is the changes in the concentrations of greenhouse gases, for which we have a relatively high level of scientific understanding. And the magnitude is reflected by this bar, CO2, methane, N2O. That's what I talk about. The halocarbons are the CFCs. Those are regulated because of the stratospheric ozone problem anyhow. And then at the other extreme, we have changes in the intensity of solar radiation that we can do nothing about. But in between, I mean, we also have stratospheric ozone, but in between we have all these other effects. It turns out that they have to do with pollution. They have to do with air quality. So it's interesting that climate change is actually connected with pollution. So what do we know about pollution? Air pollution, considered normally just a regional or local problem. We had pollution like the episodes in London that had to do with sulfur in coal that we knew was very damaging to people. Many people actually died from the pollution events in the generation of sulfuric acid and so on. But the pollution that we are more accustomed to in recent years is what we call photochemical air pollution that was really first unraveled in Los Angeles. And we know what the ingredients of pollution are hydrocarbons, like from gasoline, that are either directly emitted or gasoline that's only partially burned, nitrogen oxide, and sunlight. The combination of the three generates this type of pollution, which we know part of it is ozone, the same molecule that protects us in the stratosphere. It's actually nasty if you have to breathe it because it's very active and it irritates your lungs. And besides ozone, the other component of pollution are suspended particulate matter that we also know has very important health effects. So just in passing, I know I have very little time left, but let me nevertheless just allude to a program that we're heavily involved with that has to do with air pollution in Mexico City. We're worried about pollution in megacities of the developing world, again, because there are many cities now. So pollution is happening in many parts of the world. And this particular program, what is interesting about it is it doesn't deal just with the science and technology of the problem, but we know that we have to deal with social, economic, and political issues as well to solve these real-life problems. In this case, the science itself is not in question. We know where the pollution comes from. We still have to do a lot of science to refine our recommendations to the government, but it's very important to work very closely with the governments in these developing countries to make sure that some improvements actually take place. And that has been the case in Mexico City. It's no longer the most polluted city in the world, but there's still a long distance to go. But what I'm talking about, recall, is the context of global issues. What we have to do is to add to this pollution coming out from many cities. Recall that roughly half the population of the world now is urbanized, lives in cities, okay? And the trend is increasing there. But we have to add another source of pollution, the same type of photochemical pollution that comes from things like forest fires, but also agricultural practices such as slash and burn agriculture. Anytime you burn organic matter, you're going to generate hydrocarbons and nitrogen oxides that will contribute to this, making smoke and making ozone in the atmosphere. Now, what we know now, I'll just show very briefly some satellite views of what happens to this type of pollution. In 1998, we know there were some forest fires in Mexico. You can see the plume from a satellite clearly reaching the southern part of the United States. There were some large pollution events in Asia, again, from forest fires in 1997, and the health effects were extremely large in many parts of Asia, in this case in Kuala Lumpur. Let me show you a more recent event. This is just this year, in the end of January. This is West Africa. These red dots, this is a satellite picture, but these represent individual fires. And you can see the smoke really moving over the ocean very clearly here from the satellite pictures. One more, you can see it here, Asia, of course, Japan, Korea. Somewhere here is Beijing, and Shanghai, I guess, is somewhere around here. This gray color is pollution. So there are large amounts of pollution, and this is the same area. You can see here again Beijing and Shanghai, somewhere here covered by that. So except for the clouds, all this gray mass is pollution. This is what leads to this so-called brown cloud that there are worries that it reaches the American continent as well. How do we know that? Well, it turns out there are other events that are also very easily observed from satellites. In this case, it's not directly pollution like the one I was describing, but dust storms. And their origin, in this case, is like the Gobi Desert, which is also indirectly being affected by human activities. The Gobi Desert is increasing in size relatively fast. So desertification is another of those problems that contributes to these global issues. And you can see here the time scale for these dust clouds to reach the American continent from Asia is about 6 days. It's just how fast these things moves. And one last view graph here in terms of these pollution issues. It's also a very interesting finding. In this case, comes from this so-called Indo-X experiment. These were measurements of the composition of air. In this case, we're showing measurements about 1,000 kilometers away from the Indian continent, in two air masses that are relatively close to each other, but one is in the northern hemisphere, namely this one, and one in the southern hemisphere. And if you recall, as I explained earlier, the two hemispheres do not mix well. So this represents pollution coming from India in this case. You can clearly see the difference. You don't even see the horizon. It's pollution that has traveled 1,000 kilometers. But the effect that is really highlighted in this paper is cloudiness. Turns out that an important component of this pollution is soot, these black carbon particles that turn out to, when they are incorporated into clouds, they heat them and the clouds evaporate. So this is an example of an indirect effect of pollution. Clouds play a very important role in this energy balance of the planet. And you can either make more clouds with haze, like sulfuric acid droplets, or change their properties in such a way as to compete with the greenhouse effect, or else, like in the case of soot, you can add to the greenhouse effect in terms of decreasing cloudiness and increasing the amount of energy that reaches the surface of the planet. So all this I can label as a global air quality problem. What I have here is just a summary of, I chaired a few years ago a National Academy panel, which we labeled global air quality, to highlight these types of issues, the connection between air quality and climate change. In this particular report, we just made a point that we don't have enough observations in our planet to understand clearly how these problems come about. So we should do more about it. So I'm close to the end, but I want to remind you about these curves I showed at the beginning of constant methane, constant carbon dioxide, and then suddenly increasing. There's another curve that you all probably know about that has a similar shape. Human population. In this case, I go back many millennia, but we are now close to 6 billion people, or a little bit above, and this has all happened very recently. Fortunately, it's leveling off. Okay, it's not increasing at this rate anymore. But clearly, all these dramatic changes that I attempted to show you are a consequence of this increasing human population. So let me just finish by coming back to the ozone problem. I want to give you an example to see how we deal with these problems. As I mentioned, we dealt with the stratospheric ozone problem rather successfully. Here is an example dealing with one CFC, one that happened to be used in the past to clean electronic boards, CFC 113. When we first suggested in the 70s that these compounds had to be banned, the electronic industry got very worried. Japan was not willing initially to sign the Montreal Protocol and so on. But it turns out that society is very inventive, so many patents came about to develop these boards in different ways, to clean them even with water and soap, rather than with these more sophisticated but excellent solvents. But the most interesting technology shown here is one in which you make clean electronic boards to begin with, so you do not need to use any solvents. So let me end up with this view, again, just to highlight how thin is our atmosphere. And just to summarize a perspective on all this, of course, we know that people in the developing world, that they have to increase their standard of living. They have the right to do that. And so their economies need to grow. But it's clear that they should not grow their economies the same way that we have done it in the industrialized countries so far, because our planet is not large enough to absorb all these unwanted side products of our activities. We have to learn to do it in different ways. And so that's why it's imperative that we all work together. The industrial sector, the academic sector, environmental organizations. That's how it happened with the stratospheric ozone problem. Okay, all these sectors work together. But we have to do it once more, because these new technologies will not come out of the developing world. They don't have the resources. But at least with the ozone story, we have shown that it can be done. So there is light at the end of the tunnel. Thank you.
That was a wonderful talk, Mario. And it's a great honor to be on the program with my friend and colleague, Mario Molina. I want to thank Paul and Priscilla Gray for inviting me to be back at MIT, where I worked for 20 years until about 2 years ago in the medical department. I must confess that I have not started using PowerPoint. I'm reluctant, as you'll see, to part with things that have worked so well for me. I'm still using 35 millimeter slides. And for years, I must confess, I continued typing on my IBM Selectric when others were using word processors, and I still drive a 1986 Saab with over 200,000 miles on it. There was a slide that I believe Professor Molina may have dropped out of his tray. This is from that peer-reviewed journal called the Weekly World News. Couldn't resist that, Mario. If we could turn off the slides, I'll get back to them in a minute. A minister in Montana was tired of working on his sermon, and he decided to go bear hunting. And so he drove to some nearby mountains and hiked a trail and sat with his gun loaded. And after some hours, a large brown bear emerged and began to run towards him. The minister aimed his gun and he pulled the trigger, but the trigger jammed. And in a panic, he began to pray. And he said, "Oh, Lord, I have always been your faithful servant. Please, Lord, please, please make that bear a Christian." And at that moment, the bear came to an abrupt halt, and it put its huge paws together, and it looked up at the sky and said, "Dear Lord, I thank thee for the gift I am about to receive." Now, I tell this story because, as you'll see, I'm generally rooting for the bears, and because bears are totally unique and remarkable creatures that hold enormously important secrets for medicine, as I'll talk about shortly. Now, when I was on a flight from Washington to Boston a couple of years ago, there was all of a sudden a great commotion around me. It turned out that a large brown moth had somehow gotten onto the plane, and people, being very startled and afraid when it landed on them, wanted to kill it, even the stewardesses. Everyone was in a real frantic mood. Somehow this unfortunate animal had wandered into the high-tech, relatively sterile world of humans where it didn't belong. And people were very frightened of it, even though it was totally harmless. And everyone was very surprised when suddenly I stood up and insisted that we catch the moth and let it go. I announced this very loudly, and I must confess I surprised myself because I didn't realize I would do this, and I didn't have a very good idea of how I was going to catch the moth. But then I thought of the vomit bag in front of me, and I blew it up, and I went after the moth. I banged a fair number of heads in the process, and I released it after we landed in Terminal B at Logan Airport, where the buses were spewing their diesel fumes. I'm not sure how much of a favor this was, but I was, as you can imagine, savoring one of those few moments in life when people ask, "Who was that masked man?" Or perhaps in this case, "Who was that madman?" But I tell this story because it illustrates, it seems to me, how separated we've become from the environment in which we live. So disconnected from the natural world which increasingly exists as we become more and more urbanized in zoos and aquaria and botanical gardens. So disconnected that true nature, like the moth, seemed to many an alien creature, as a hostile force to be conquered and exploited and even killed, that the environment has come to be, for many people, an infinite resource that exists for our use alone, that we can take as much as we want from, or as an infinite sink that we can dump as much as we want into, that somehow we can alter and degrade the atmosphere and the oceans and the forests and soils, endangering perhaps millions of species we share this planet with, some of which have been on Earth for hundreds of millions of years longer than we have, like sharks and dragonflies and horseshoe crabs and frogs, as if somehow these alterations had nothing whatsoever to do with us at all, as if we were totally insulated from them. And it seems to me that this lack of connection to the environment, this fundamental failure to understand that our health and lives depend on the health of the global environment, that this problem is among the most important problems we face in the years ahead. Now, what prevents us from recognizing the threat that global environmental change poses for us? For one, it's too abstract. It's too hard to relate to. As you heard Professor Molina talking about the atmosphere and the globe, it occurs over too large a scale. It evolves too slowly over time. It's outside our everyday experience, especially for those of us in rich nations like this one, not living at the margin of survival, as large numbers of people in developing countries do all the time, at the mercy of every cyclone or crop failure. Global environmental change is also too frightening. The specter of floods or drought or fires or famine or epidemics of infectious disease, they're too overwhelming to contemplate. They're biblical in their proportions. And for the most part, the problems seem too large to solve, making people feel frightened or helpless or hopeless, and they'd rather just as soon think about something else. They're also very complicated and technical. The science is very complicated, and it's made worse, it seems to me, by scientists and also people in public health who write and speak in jargon-filled languages, unable to communicate with policymakers or the media or the public. So people find it generally too hard to understand. And it's also too hypothetical. It's only a theory in the eyes of some skeptics, a result of the difficulty, as Professor Molina talked about, of coming up with cause and proof of cause and effect. The reality that there are large natural fluctuations and the fact that there's only one Earth, and we've never been in this situation before. There is no controlled subject for global experiments that are now taking place, no other Earth where the variables can be held constant. So we have to rely on computer models and projections that are sometimes, as you know, less than convincing. For many, it's also not worth worrying about. They believe if science got us into this mess, it's also going to get us out. We'll invent or synthesize or engineer our way out of all of our difficulties. And while science has much to offer, we must be very humble and fully aware of its limitations, especially in the face of understanding highly complex nonlinear systems. As you heard Professor Molina talking about chlorofluorocarbons, which were originally greeted as the most wonderful chemicals for refrigeration ever. They were not toxic like ammonia, they were not flammable like propane, the refrigerants that were used at the time, and so chemically unreactive that no one thought they would be an environmental problem at all. And furthermore, in contrast to the issue of nuclear weapons, which I spent many years working on, where there were no changes that we had to make in our lifestyle or in personal choices to reduce the threat of nuclear war, with global environmental change, we're all part of the problem and we're all part of the solution. And many of us, including myself at times, would just as soon not think about or try not to learn about the contribution our SUVs or teak furniture or eating farm-raised shrimp or Atlantic salmon, both of which, by the way, I love, make to damaging the environment. And finally, there are powerful forces in some businesses, some in the fossil fuel industry, some in timber and mining and cattle farming and chemical manufacturing and land development, et cetera, and their political supporters, including some scientists, some of whom are clearly motivated by reasonable scientific questions, but others of whom represent vested interests, motivated by greed, I'm afraid to say, who have attempted, much as the tobacco industry has done for decades, to suppress scientific findings that raise health and safety questions about their practices and products, and who have tried to undermine the credibility of respected scientists and public health experts. And these skeptics, I'm sorry to say, are often given equal time by the media, which loves a good fight, as if they represented objective, widely held, carefully researched, equally valid scientific viewpoints, which they do not. So the public is often confused and doesn't know what or whom to believe. Well, it was in recognizing the scope and magnitude of these barriers that made it difficult for people to grasp what human activity was doing to the global environment that we founded the center that you heard Professor Gray mention at Harvard Medical School, believing somehow that physicians and health professionals, that we could perhaps help translate this abstract technical language of environmental science into the concrete personal terms of human health that we hoped people could relate to and understand. And that by helping them understand the potential risks to their health and lives and to those of their children, we could perhaps help motivate them to make the changes in their personal lives and to support the policies necessary to really protect the global environment. So I thought that this evening I would go over one of the main areas of interest at our center at the medical school, Harvard Medical School, and the area that I'm most involved in. That's the issue of loss of biological diversity and its implications for health. Now, when Homo sapiens evolved some 130,000 years ago, the number of species on Earth was the largest ever, but human activity has resulted in species extinction rates that are maybe 100 to even 1,000 times those of pre-human levels, causing Ed Wilson and Paul Ehrlich and others to estimate that we could lose maybe 25 to 40% or more of all plant and animal species presently alive in the next 50 years, and as many as 2/3 of them by 2100 if these rates persist. And it's not just in the tropical rainforest, but in temperate regions as well, like the United States in this map. The dark states have the greatest loss of species. There's some 500 known animal and plant species that are either missing or are known to be extinct since the 17th century. And the greatest are found in states like California and, of course, the island of Hawaii and Alabama. And the greatest losses are in some freshwater species like mollusks and crustaceans. What's interesting is that the United States is incredibly rich biologically. We lead the world in the diversity of salamanders, crayfish, freshwater turtles, freshwater mollusks. We have the most species of mammals and among the richest flora of any temperate country in the world. Now, the causes of species extinction are many. The main one is the degradation and the reduction and the fragmentation of habitats, especially in species-rich areas like tropical rainforests and coral reefs. But we must be aware of other factors as well, such as global warming and the associated changes in global climate. Let me say a word about this critical issue, which Professor Molina has touched on. 1998 was by far the warmest year since 1856, when average annual global surface temperatures were first accurately measured. This past year, 2002, was the second warmest. 2001 was the third warmest. 1997 was the fourth warmest. 1995 was the fifth warmest. 9 out of 10 of the warmest years on record since the mid-19th century have occurred since 1990. And it is clear from measurements that we have that average global temperatures have increased, as Professor Molina said, roughly 1 degree Fahrenheit since 1880 or so when the Industrial Revolution began. Now, these projections that Professor Molina mentioned on this is the last 20,000 years. In IPCC2, they were in this range, going up to, say, 3.5 degrees centigrade. IPCC has so far raised that at the upper limit to go as high as 11 degrees Fahrenheit. And as Professor Molina mentioned, that degree of change is the difference between the end of the last ice age, some 20,000 years ago, and now. And at the end of the last ice age, where we're sitting in this lecture room, we were under a layer of ice a mile thick. So we're talking about huge, huge changes in temperature. Now, what's important for species is not just the magnitude of this change, but the rate of it. And it is thought to be somewhere between 10 and 100 times greater than temperature warmings in the past, posing great risk to species. Now, why is this? Well, the fossil record shows that climate change was the dominant factor in the great extinctions of the past, both warming and cooling, directly because the temperature shifts were outside the ranges to which species could adapt, but indirectly because of changes in habitat, formation of glaciers, changes in sea level, etc. With warming, species on land and in the oceans move towards the poles. Their ranges change, and on land they also move to higher altitudes. And with cooling, they moved back towards the equator and to lower altitudes. Those that couldn't shift fast enough, or because there were barriers to their movement of their range change, were lost. Now, there's a much faster rate of change predicted, and there are barriers everywhere that humans have created, farms and cities and roads, etc. Now, you recall in that previous graph that the temperature has changed roughly 1 degree Fahrenheit. So the question is, can we see any evidence of biological changes with this small degree of temperature increase on average? And the answer seems to be yes. There are 2 major reports in Nature in the last month or so that are showing what are called fingerprints of biological ecosystem change from climate change. And these are events like the earlier arrival of migratory birds or frog breeding, earlier spring flowering, early budding in trees, and also changes in the ranges of animals, like I mentioned. For example, this is what's called Edith's checker spot butterfly. It's a butterfly that's in the western part of the United States, and in the last several decades, its range, it's been followed very closely. Butterflies and birds are very closely studied by biologists, mostly because they're beautiful, in part. And its range has moved northward in the western United States. It's been tracked for decades. And the same has been true with vascular plants moving to higher altitudes in the Alps. These are both very carefully done studies in the literature. Now, there are other factors, clearly, besides climate change that lead to threats to species. One of them, of course, is toxic chemicals, which may lead to reproductive or endocrine or immunologic or developmental effects, and they may cause species loss, like in this study with frog species that grow extra limbs, and of course that affects reproduction, et cetera. And of course, invasive species like the zebra mussel or the purple loosestrife or others, which affect species survival. And finally, just the wanton slaughter of many species, such as these gorillas in Western Africa, which along with chimps and other primates are being killed for bushmeat to feed loggers and miners, but also native tribes, many of which are very hungry and poor. I won't get into it, but one of the, it's quite strongly believed now in the scientific community that the source of HIV/AIDS came from a subspecies of chimpanzee in Cameroon from bushmeat exposure, that is, exposure to blood over last several decades, and has led to catastrophe, as you know. Now, what does all this have to do with human health? Well, for one, with the loss of species, we're losing the possibility of discovering new medicines, because over the course of billions of years of evolution, species have developed chemicals that they need to fight infections and tumors and other diseases, and also to capture prey and avoid being eaten. And some of these chemicals have become some of today's most important pharmaceuticals. This is what's called the cinchona tree from the Amazon. It gave us quinine, and another compound called quinidine. Quinine is a major anti-malarial. It was the original anti-malarial. It's making a comeback as some of the plasmodia from malaria are developing resistance to synthetics. Quinidine is used to treat cardiac disease. But temperate species have also given us enormously useful drugs. The wonder drug aspirin was originally derived from salicylin extracted from the willow tree, which really everybody in this room over 50, unless it's contraindicated for other reasons like a bleeding disorder, should be taking one aspirin every other day. There's extremely robust data in the literature that this prevents heart attacks and strokes. And just in the last week, there have been two published studies about aspirin, this incredible drug, that it's thought to protect against throat and mouth cancer, and in today's New York Times, to prevent the growth of precancerous polyps in the colon, which is a major killer. Another temperate source of drugs is from these flowers called foxglove. This is a picture from my garden. This flower gave us digitalis, and also which is widely used in synthetic analogs to treat congestive heart failure and atrial fibrillation. Indeed, a study showed that of the 150 most prescribed drugs in the United States, more than half of them were either derived from or patterned after compounds derived from natural sources. And of course, as you know, in the developing world, some 80% of people rely on traditional medicines mostly from plants. Now, I want to talk about this species, this genus. They're called cone snails. These are extremely beautiful shells. They've been collected for centuries, brought great deals of money during the Renaissance in Holland. In fact, one cone snail was sold at an auction for more than a Vermeer painting in 1796. They were so highly prized. What's incredible about these, there's some 500 species. They're predatory snails. They mostly live in tropical coral reefs in the South Pacific, and they feed by and defend themselves by firing a poison-coated harpoon. And this spike contains a cocktail of toxins. They paralyze their prey, worms and mollusks and fish. These are small peptides, much like the peptides that are found in the toxins of snakes and scorpions and spiders and sea anemones. But in cone snails, they are truly amazing. There are 500 species. Each species is thought to contain 100 distinct peptide toxins. So there may be as many as 50,000 peptide toxins. Only 100 have been characterized from 3 species. And of these 100, I want to tell you about one in particular, which is what's called a voltage-sensitive calcium channel blocker. You may know about another calcium channel blocker, which is used in the treatment of angina or high blood pressure, called Kalan or verapamil. This calcium channel blocker does 2 remarkable things that have been studied. One is it blocks a cascade of biochemical reactions that have been mediated by the influx of calcium, and that starts the death of nerve cells when there hasn't been enough circulation. So this is of tremendous interest in coronary bypass surgery and following head injuries. But it also, this is firing this harpoon on a fish. But it also binds to the incoming nerve cells in what's called the dorsal horn of the spinal cord with enormous specificity and blocks the transmission of pain up these neurons without blocking fine touch. Now, what's amazing about this particular synthetic drug that's coming from the toxin is that it's been shown to be 1,000 times more potent than morphine. But unlike morphine, it doesn't cause addiction or the development of tolerance. This is an enormous problem in treating chronic pain in people with nerve injuries or cancer or AIDS, HIV/AIDS, because what happens is you need more and more drug to get the same effect because of the development of tolerance. This particular toxin-developed drug does not seem to cause that. Other cone snail toxins are being developed for epilepsy that doesn't respond to other epileptic medications and for the treatment of a kind of lung cancer that has been so far unresponsive to other treatments. But yet cone snails are endangered. Their shells are collected both for marine curios and also for, unfortunately, for medical research. There's very little regulation. But mostly cone snails live on coral reefs, and coral reefs are endangered around the world, particularly in parts of the South Pacific where they are mostly found. Now, species loss doesn't only lead to a loss of potential medicines. It affects medical research in major ways. I mentioned about bears, and bear populations are threatened in many parts of the world because of destruction of their habitat, but also because of overhunting, secondary to the high prices their organs, reputed to have medicinal value, bring in Asian black markets. Bear gallbladders, for example, are highly sought after. They are worth 18 times their weight in gold. And there's a flourishing black market trade in bear parts in parts of South Korea and China and here in Thailand. And yet the tragedy is that living bears are worth far more than the sum of all their body parts. Let me explain why. In winter months, bears enter a 3 to 7 month period of hibernation. It's really denning. They don't fully hibernate as some rodent species do. Their heart rate drops and their temperature drops, but they are fully arousable, as some bear biologists have discovered to their dismay. Despite a lack of weight bearing, for months, denning bears don't lose bone mass. They don't develop osteoporosis, a phenomenon that occurs in every other mammalian species, including humans, with decreased mechanical use of the skeleton. Osteoporosis is an enormous problem in the inactive elderly, especially postmenopausal women and paralyzed patients. And understanding how bears prevent it, there's a lot of research going on, prevent their bones from being resorbed could lead to new ways of preventing and treating this disease, which afflicts 28 million people in the United States alone, results in 1.5 million bone fractures and about 70,000 deaths every year, costs the U.S. economy $13.8 billion a year in medical costs and lost productivity. Bears also don't eat, drink, urinate, or defecate for periods of up to 7 months. If we don't urinate for a few days, we die. They are able to recycle their urinary waste. They make new protein. They have a pathway that we don't fully understand. They recycle everything. And kidney failure in the United States costs the U.S. economy an additional $16 billion a year. The only way to treat someone with terminal kidney disease is dialysis or kidney transplant. We have no other treatment. Let me just say a quick word about polar bears, which are endangered for yet another reason, not just destruction of their habitat, which from things like oil exploration and drilling and in the Arctic National Wildlife Refuge where they live, but also overhunting. Some hunters pay up to $22,000 to bag a polar bear on expeditions, but they're also being endangered by climate change, which, as Professor Molina said, is not uniform. Is greatest in boreal regions and at the poles. And this is an enormous problem for bears because ice thins. They depend on ice to hunt seals, and that's their main food. If there's no ice, the seals can surface anywhere far from the polar bears. Just one quick thing before moving on. I know I'm over time a little bit. Other species don't only teach us about medical things, but teach us other secrets. This strange building is from Harare, Zimbabwe. It's modeled after the venting and air circulation dynamics that are found in termite nests. Termites, it turns out, are farmers, and they grow a fungus in the middle of their nests, and they have to keep the fungus at a constant 87 degrees Fahrenheit, plus or minus a half a degree, despite very wide fluctuations outside in this part of Africa. Some can get to be 35 degrees Fahrenheit at night and over 104 degrees during the day. This Harare building is modeled after those dynamics of airflow and humidity and uses 1/10 the energy that a building of its size would use for heating and cooling. Now, finally, I want to talk about the whole issue of ecosystem services, and that is the ways that species interact to provide valuable life support for all of us, for all living things. They maintain global temperatures and precipitation by storing carbon. They regulate atmospheric concentrations of oxygen and carbon dioxide and water vapor. They break down wastes and dead organisms. They return the nutrients to the land and the oceans. They pollinate plants, et cetera, et cetera, et cetera. We don't know a great deal about how some of these ecosystems functions work. Let me talk about one of them from a human point of view, and that is to hold infectious agents in the environment in check so they, from our perspective, don't cause significant human disease. This is a map of Lyme disease cases, and in the United States, each dot represents a case, and you can see, of course, the enormous concentration in the Middle Atlantic and New England, and some in the upper Midwest, spattering of cases in California and in parts of the Southeast. What you notice, well, let me go. It's, Lyme disease is carried. It's the most common vector-borne disease in the United States. There are about 19,000 reported cases, probably many others that aren't reported. It's carried by the black-legged tick in the east. It carries a bacteria, a spirochete. Also involved in the disease are the white-tailed deer and also the white-footed mouse. I'm sorry to say this is a deer mouse, but I didn't have a picture of a white-footed mouse. We are an accidental host, and it's long been observed, as I mentioned, that there are not that many cases in the western part of the United States, even though there are ticks and there are spirochete and there are deer and there are mice. It turns out one of the favorite meals for the tick out west is something called the western fence lizard, and its blood contains a substance that kills the bacteria. Many species of reptiles are threatened, and one has to ask what happens if we lose the western fence lizard to Lyme disease incidence out west. But another issue is quite interesting, and that is in areas where there's little biological diversity, like in islands like Martha's Vineyard and Nantucket, rates of infection are very high. And some very elegant work by one of my colleagues, Rick Ostfeld, has shown that when there's a great deal of biological diversity of vertebrates in the forest, then the chances of getting Lyme are less. And the reasons are quite interesting. One is that the ticks bite anything they find, that they come across. So they're not only biting the mouse and the deer, which are part of the cycle, they're also biting other vertebrates. They're biting birds, they're biting amphibians, they're biting whatever crosses their path. And these other animals are what are called incompetent hosts. They don't keep the life cycle of the Lyme going. So there's a dilution, what's called a dilution effect of the bacteria, and we're less likely to get Lyme if there are lots of different other animals in the forest. But what also happens is that some of these other animals are competing with the main host, the mouse, for food, so they keep its population down, and some of them are predators. So an example where biological diversity keeps the risk of Lyme low. Now, what does all this mean, and what can be done? And I may be putting on my more activist hat in this section, but I will wear it gently. I must tell you that I came back from London late last night, so it is now, what is it, 8:30, well, 5 hours later. So after 1 o'clock, I'm not responsible for anything I think or say. So, well, for one, we have to look at these problems directly, without avoidance and denial, no matter how difficult or even frightening they are, in order to begin to solve them. We can't bury our heads in the sand or say it's up to others. We must help people in the business world and in politics to see that it's not a choice between a healthy environment or healthy profits. One can have both. Indeed, without a healthy environment, the cost to society from the impacts on agriculture and private property and human health will be so enormous as to affect every aspect of the marketplace. And as we did with the Montreal Protocol, as Professor Molina said, that protected the ozone layer, the United States, as the most powerful player on the world stage, as the greatest consumer of resources and producer of waste, we must take the lead in world efforts to reduce greenhouse gases and to protect biological diversity. We have not even signed and ratified the Convention on Biological Diversity, which almost every other country in the world has. We don't have a seat at the table at the convention. And as you know, while 178 nations agreed last year to curb greenhouse gas emissions, including all of our allies, the United States, with 4 to 5% of the world's population, producing 25% of the world's human-released greenhouse gases, sat on the sidelines. And in my view, this should be a matter of national disgrace and great embarrassment. And it may be said that those who are blocking these efforts by, I believe, deliberately misrepresenting the science in some cases and trying to discredit people on the National Academy of Sciences or the Intergovernmental Panel on Climate Change, like unfortunately some members of our administration and some in Congress, who have, I'm afraid, appallingly meager understanding of the environment or of public health. And I'm afraid also, and this is where I may get into trouble, but some multinationals like ExxonMobil, which in their bi-weekly infomercials in the New York Times talk about climate change science in an often very misleading way, or some, quote, think tanks like the George C. Marshall Institute or the Competitive Enterprise Institute. It may be said of them, as Teddy Roosevelt once said of his political opponents, quote, that every time they open their mouths on these issues, they subtract from the sum total of human knowledge, end of quote. And we should not be surprised to learn that our species, Homo sapiens, has been found to contain some Neanderthal genetic material. Well, so much for my rant. We can and we must invest scientific effort and money on a scale similar to the Manhattan Project to develop renewable, non-polluting sources of energy, solar and wind and geothermal, new batteries, greater efficiency. Why isn't the United States leading in these technologies? I'm afraid to say, why isn't MIT leading in these technologies? Isn't it clear that those who succeed in developing inexpensive, efficient, renewable energy sources will be the next Microsoft, the next Intel? We must control the discharge of pollutants, particularly those that are long-lasting and accumulate in the food chain, like some heavy metals and some persistent organic pollutants. We must, as you saw Professor Molina's slide, control or slow down population growth by supporting efforts to provide access to family planning to every woman who wants it, and by increasing educational and career opportunities for women around the world. We need to protect biologically rich ecosystems like tropical rainforests and coral reefs. And let me say just a quick word about these. One of the greatest crimes against the environment has been the draining and destruction of marshlands of southern Iraq by Saddam Hussein, and the destruction of the 6,000-year-old culture of the Marsh Arabs, which developed the arch thousands of years before the Romans. But it is a tragic irony that the U.S. Army Corps of Engineers, with the blessing of the Bush administration, has begun to redefine what constitutes a wetland, so that plans are now in the works to drain hundreds of thousands of acres of wetlands across coastal Mississippi and parts of Texas so that they can be developed. And I should say, if there is a war in Iraq, it will be devastating, not just for the tens of thousands of Iraqi civilians or the thousands, perhaps, of American and British young people, but for the environment. We must ourselves be models for responsible, healthy, sustainable environmental practices by reducing and reusing and recycling resources. Do we really need every gadget that the newest, sharper image catalog shows us? I believe we need to drive small cars. That's my wife, Jake, standing next to this little Fiat. She is 5'11". She would kill me if she knew I was showing this picture. rather than this one. God, I hope this is not made by Ford Motor Company. I don't think so. I don't think so. I think it's a Chevrolet. Uh-oh, I feel another rant coming on. Let me just say a quick word about SUVs. They consume 2 or 3 times as much gasoline as a compact sedan. They give off 5 times more air pollutants. They're 3 times more likely to kill the other driver in an accident and 2 to 4 times more likely to roll over when hit. But I'm delighted to say that Ford Motor Company is taking a really leadership role in developing safer and more fuel-efficient SUVs and working on fuel cell vehicles, and I'm very proud of that. Clearly, one of the moves is to look at hybrid vehicles. This is the Honda Insight, which gets roughly 60 miles to a gallon in some tests. But better yet, take public transportation or bike or walk. And there are other ways we can reduce our consumption of energy. We can better insulate our homes. We can use more energy-efficient lighting. If every household in California had replaced just 4 75-watt light bulbs with available compact fluorescent bulbs, the state would not have had to build 3 new average-sized power plants. And in the energy crunch, and this should be somebody's PhD thesis in this room, in 2001, during the blackouts and brownouts in California, the state residents reduced electrical use by 11% without a significant change in their quality of life. Who is studying this? Who is cataloging this? This is not rocket science. These technologies are available now. We need to engage in a whole array of individual and collective actions that preserve biodiversity and the environment, and we need to be a model for others. It's hard to be one to tell family and friends that they shouldn't eat that piece of swordfish. One is not generally invited to too many more family parties. But it is important to say politely and without being condescending or environmentally holier than thou, some things like that. We can eat low on the food chain. We should avoid marine species that are endangered, like orange roughy and Chilean sea bass, which was renamed. It's really Patagonian toothfish. We shouldn't eat these. They're endangered fish. The Monterey Bay Aquarium puts out a list of fish that are not endangered that you can eat. We should stay away, I'm sorry to say because I love them, from farm-raised carnivorous salmon. It takes 7 pounds of fish meal to make 1 pound of farm-raised salmon. And you can buy frozen wild-caught salmon from the Pacific Northwest in Alaska. You can buy herbivorous catfish or tilapia. You should anyway be eating low on the food fish web because higher you go, the more likely you are to be exposed to pollutants, which get bioaccumulated. We should eat less red meat. It's not good for the environment, and it's not good for you either. And if you do buy meat, buy organic meat, because then you won't be getting growth hormones or antibiotics or pesticides, and buy organic food anyway, because food from local farmers at farmers markets, this will encourage organic food practices and keep these farmers trying to preserve the environment in business. And try to avoid, I'm sorry to say, because it has effects on the developing world, but buying produce that had to fly 5,000 miles to get to you. You should be buying as much as you can. I know it's not always possible, things that are local. Don't buy tropical hardwoods like teak or mahogany unless it's clear that these are being raised sustainably. And ask about that. Home Depot is selling certified wood products, and you can also buy recycled wood. It's available in many areas for construction. And save energy. Clearly, as you've heard Professor Molina say, global warming will become, in synergy with other forces, the predominant factor in coming decades for species loss. When the environmentalists in Cape Cod and the islands protest the wind-generating towers, saying they'll harm marine species and birds, I agree that we need to study this and mitigate these effects, but are they considering the effect on climate change on marine species and birds? And what other practical suggestions do they have to reduce our greenhouse gas emissions and still meet our energy needs? All of you, we can reduce our own energy use. For God's sakes, turn off the lights in rooms that are empty. Turn down the thermostat at night. Wear a sweater. Walk, bike, take the train. Above all, we need to become fully informed about these issues and help others understand them. It's not too late to apply the brakes. This is a real picture in the Gare du Montparnasse in Paris, where this train unfortunately did not apply its brakes in time. Pleased to say our center has focused all of our energies on trying to achieve some of these goals. We have taught a course for 6 years at Harvard Medical School called Human Health and Global Environmental Change. Professor Molina has spoken in the course on ozone depletion, Ed Wilson on loss of biodiversity. We bring people from all over the country and world to speak. It's open to students at MIT. And you'll be there with Harvard medical students, students from the Harvard School of Public Health, the Kennedy School, and other schools. It's very highly ranked, and it's also completely online on our website. All the lectures as streaming video, all the readings as PDF files. Anyone in the world with at least a 56K modem can take the entire course free of charge, and hundreds have around the world. We do work on the Congress. We've held 8 congressional briefings so far, the last one on bushmeat in primates and HIV/AIDS with Jane Goodall. That's also completely on our website. Every year in the spring, we hold an intensive course on the environment and health for congressional staffers, which has become very popular. And because of that, we've been asked to design a course for broadcast meteorologists on television and radio about the links of climate and weather to the environment and human health. We're working on an exhibit at the New England Aquarium on oceans and health, and we're working on this project with the United Nations on biodiversity and human health. Well, I want to close with a final personal comment. I believe we are incredibly lucky to be alive at this moment in history. For the changes to the environment that I've spoken about are caused by our own behavior. And we have the ability, our generation, especially those of us in the most powerful country on the planet, especially those of us in this room who are among the most privileged and influential members of this society, we have the ability to turn these changes around. I believe that for the global environment, and that in destroying other species and ecosystems and degrading the global environment in which we all live, we're doing something that is not just morally wrong, it is deeply and shamefully ignorant. For we're tampering with life support systems of the planet, with the physical and chemical and biological systems of this earth, in ways we barely understand, that are bound to have profound consequences for the health and lives of our children, and for all children to come. We can and we must protect this incredibly wondrous gift that we have been given, and I urge all of you to join me and my colleagues in this effort. Thank you.
Mario and Eric, thank you very, very much. We've had here this evening lucid descriptions of the issues that face us, 6 billion of us, and what we are doing to our environment. And we've had clarion calls to what we must, the ways in which we must take action. I hope that all of us, as we leave here tonight, will think on those calls to action and push in directions that will ameliorate the changes we are forcing, 6 billion of us, on the environment for our children and grandchildren. We have a few minutes for questions here. There are 2 microphones, one at the foot of each aisle. This is being video cast, so I'd appreciate it if people who want to speak would come down to the microphones, and Professor Molina and Dr. Chivian will respond. Yes, sir.
Hi, I was wondering if you could just say a word about some of the scientists, and I know they're a relatively small minority, who would dispute some of your findings. And I'd also like to ask if you think that one of the main reasons why people don't realize what's going on, the average person, is because they think that science is black and white, and they don't understand that in general, science is always in a state of flux. And there's an old saying that it only advances one funeral at a time. And so how can this kind of information reach the public? Because if everyone in the public were here listening to you tonight, no doubt, they would feel very differently, and if they understood what the scientific consensus is, the vast majority of scientists and how they think.
Let me start with him. Okay, I think this is a question we should both answer, but let me give a brief first answer. I think part of the explanation is there are, of course, some scientists that have some special interests, okay, and so maybe you can explain part of their behavior because they want to protect those interests. But there are other scientists that appear to be in good faith. They question what's the sort of things that we talk about. And in my opinion, some of these apparently divergent ways of responding to what's going on around us have to do with one of the points I tried to make of what is science and what is not science. For example, in order to assess the question whether you should worry about these issues, you also have to take into account what are the consequences of certain actions. Will the economy suffer? Well, if we talk about uncertainties in the science, there are even larger uncertainties in terms of how the economy will respond to suggested changes. From the example with CFCs, there were people that worried that millions of jobs would be lost and billions of dollars would be lost. That turned out not to be the case. So in my own personal experience, that was exaggerated. But something similar can certainly happen with a climate change issue. With biodiversity, I guess much of it is really ignorance. There are not many people that are sufficiently well informed to realize how much in trouble we are, as Dr. Chivian really explained very clearly.
Am I still on? I didn't mean to imply in any way that scientists who disagree with some of the things I said are not doing that out of valid scientific questions. Clearly, there are many that are. I do believe that with the issue of climate change and loss of biodiversity, there's pretty great consensus in the scientific community that these are real problems and great agreement about what is at stake. But I want to tell you an anecdote which was really quite revealing to me. I go to the Congress a few months before designing this course for congressional staffers, and one of the aides in giving his ideas about what lectures we should hold mentioned that we should go to this one of the think tanks that I mentioned and bring in one of the other views on climate change to balance out the view that we might have from someone who was part of the intergovernmental panel. And one of the things he said I found very disturbing, and it revealed to me how little understanding there is about the way of the working of science and how science should really advise policy. He said, well, that person has as much as valid a view, hadn't published anything in the peer-reviewed literature, but has a strongly held view, and it's equally valid to someone, say, from the IPCC or the National Academy. And he said, it's just a point of view. It's a belief system. That is, science is one belief system, and another skeptical point of view that is not necessarily based on science is an equally valid belief system. And I think that really is our fault. Because if there's that much, this is a fairly senior aide in a very senior office in the Senate. If there's that much misunderstanding about how science works, because as you have said, Mario, and I think you've implied, the uncertainty is interpreted as a point of view. You know, that if science is not if you can't prove cause and effect, then you really have no more reason to state that view than someone who has a different point of view. I think we're not doing a terribly good job in communicating with policymakers or the public, and I think we really need to think more about how to do that in a way that is understandable. And because of this view, we're going to have a whole morning session about how science works, how hypotheses are tested, the issue of uncertainty, because I think there was so little understanding of the role of science.
Yes, please.
It's a great honor to be here because I've taken classes with both of you. I'm a student of both of you. One of the things that often was brought up in the course at Harvard, as well as brought up again and again in the scientific community dealing with environmental issues, is the role of the media in communicating information to the general public, raising awareness. And of course, connected to that is the role that scientists have to play in making sure correct information and easily understandable information is given to the media. And that there seems to be a certain degree of misunderstanding how that should be done. Scientists somehow think that just science is so clear, that the facts are so clear that you just put it out there. And a media person from New York Times or Newsweek, whatever, will pick it up and be able to deliver the right way. Could you say a little bit about the responsibility of people who are studying this field in actually taking time out and spending time with the media, or having an outreach to really make people understand not just the fact that science is factual and based on experiments done, but also that it actually relates to everyday lives?
Sure. Okay, let me start with some comments there. I agree with you. We scientists do have a responsibility to communicate, particularly with the media, because that's one way to communicate with the public. There is, however, some sort of tradition which I think is disappearing, but the tradition in the old way of doing science is to consider yourself above the masses, and so you develop a language that only your peers can understand, sort of the ivory tower image. If you exaggerate that, that's even where this sort of thinking comes, that if your science has some sort of application, it becomes dirty. It's no longer a pure science, as if though there's a pure and an impure science. Okay. But in any event, I'm very much in agreement with you that it's important to be able to communicate your science, particularly if the science can have impacts to society. And one more point, which actually connects this view with us being working at universities and trying to teach. I think if you really understand well some of the problems that you're dealing with, you should be able to put it in plain language. It does require a very clear understanding. Okay? And it's not easy. You have to work at that. But I guess we both have spent quite a bit of time talking to reporters, and we've learned how to communicate with them. Fortunately, at least here in the United States, now there are societies of environmental journalists. Okay? But it takes time. It takes an effort. You have to develop some sort of a connection with them. So it's a continued effort. We cannot give that up. But we should really train all our students to be aware of the problem and to try to be able to explain their findings in common language. I think it's an important thing to do.
I totally agree. And there is a group called the National Association of Science Writers. It's quite large. It has its annual meeting during the AAAS meetings, and there also is this environmental science writer group. They're very interested in speaking with people in the sciences and public health. And as Professor Molina said, I think we need to be very cognizant of the language we use so that they can really understand it. There's almost nothing more important than that, in my view, because they are reaching millions of people. But I did want to go back to this point I made before. I think there's something sort of fundamentally amiss with some of the reporting about science and about any issue, because the media in many ways is structured to have opposing views. Nightline is the prime example. So that someone from the National Academy of Science talking about climate change will be debating someone like Rush Limbaugh. And that kind of fight, that kind of sort of polar opposite, polarizing of views, is something that our media, and I think not just our media, but other media, tend to lean to, because it's sort of, it's watch journalism. I mean, we can see it on, what's that program where everyone's shouting at each other all the time? So that kind of polarization of views tends to give the impression to the viewer that these are two equally valid viewpoints, even if one is very far over to one side. And that's a real problem, I think, in terms of public understanding.
Last question at this microphone.
Hi. I know that where I live, for one, we seem to heat our rooms with the air exhausted from the cooling fans of our Pentium 4 Linux boxes. And I was maybe curious on a couple counts that first I was wondering if either of you ever had any personal guilt attacks that something you're doing was being environmentally destructive. I know driving the saw maybe better than driving an SUV. But it could be still better. Could be definitely be far still better. I would love to retrofit that saw with fuel cell engines. But I was wondering first if there were any personal guilt attacks that you had experienced in that regard, and on the other hand, if there was anything, even anything anecdotal that you consider noteworthy, a situation you have personally ameliorated.
Okay. Well, let me start with I'll just make the statement, I have had guilt attacks. But there are many things we can do personally. However, what I worried about in terms of having the most impact possible on the way things function is to communicate directly with our decision makers. That doesn't mean we still shouldn't do personal things like Dr. Chivian very eloquently put. But some of the roots of the problem, say you mentioned about some situations with energy. Some of the roots of the problem is that energy is just far too cheap because it's not really considering the actual costs of environmental effects. Okay, this is what we call externalities, and they can be brought in. So just to give you an example how I sort of counteract these guilt attacks, I belong to a group now, an energy commission, which is non-partisan. We have people from all spectra, industry, Republicans, Democrats, and so on. And one of the achievements of this group, and I must say I'm an advocate in that group, is to come up with a recommendation such as this one, that energy should be more expensive. Doesn't go along the current thinking of the administration. But if a group like this makes strong statements, and it's clearly not an extreme liberal leftist group, I expect it to have a large impact. So to me, that's an important action, but there are lots of things personally that we should be doing. Perhaps I should let Eric do the other part.
Well, if I didn't make this clear before, I'm a psychiatrist. I practice clinically. It's always very difficult to ask a psychiatrist how he or she is feeling about anything. And if you ask us about guilt, let me tell you. No, I clearly, I mean, I used to drive my car to work until my wife shamed me, and you know, we have a battle. I turn off lights in the room, but she walks everywhere. So now I walk everywhere. Clearly, all of us can do things better, but I actually think guilt is not a good motivator for change. I think if you speak to an audience and you make everybody feel guilty about what they're doing, that's not going to get anywhere. I think people get their backs up, they get defensive, they rationalize what they're doing, or they turn you off. So I don't think that is a good way. And you know, we've struggled with this in the work we've done with nuclear weapons and with the environment. I think what people need to hear is that, one, the situation is not hopeless. There are things that we can change, and there are things that will have great benefit and value, and that all of us are a part of the solution, and that added collective value has great benefit for society. So I think that's a much better way of approaching these issues. But
since I have the floor still, I would like to propose, since, if I remember from my late teens and early 20s, I loved competition and was competitive. And I would love to see MIT dorms compete for who can have the best recycling program, which dorm can use the least amount of energy per capita. Why not have something like that? Or which dorm at MIT can use less energy per capita than a dorm at Harvard? Or Caltech?
Two quick matters before we adjourn. The next lectures in this series, the Ford MIT series, will occur here on the, not in this room, but on the 23rd of September. The two speakers will be two institute professors, Philip Sharp from the Department of Biology and Jerome Friedman from the Department of Physics. And the title is National Security Issues and the Impact on Research. There is a reception following this meeting in the Bush lobby, Building 13 lobby, which is about 50 feet in that direction. If you go out into the corridor behind me and go down the stairs at the end of that corridor, it'll bring you right into the Bush lobby. Please join me once again in thanking our speakers.